So thank you very much, Bob. After these insights into the history of time, you might feel thrown into opposing extremes, as expressed by E. E. Cummings. So what time is it? It is by every star a different time, and each most falsely true. Or so subhumans, superminds declare. Our next speaker, Professor John Leonard, is a professor of physics, and like some physicists, he belongs to the rare group of subhuman superminds. He will address a more worrisome idea, namely, do some people age faster than others?
So I'll use this. Good evening. So I get to take up the story at the beginning of the 20th century and lead you on the world's shortest course in relativity. And so let's see where that laser pointer went. Here we go. So this is, many recognize this as a botched up Escher picture with Starbucks everywhere, you know. No matter where you go and which way you're tilted. This was the first experiment that showed that, as we'll talk about, light has the same speed wherever you measure it. From whatever place you're measuring it, you will get one velocity for the velocity of light. This is the Michelson-Morley experiment, and it measured the velocity of light going one direction and the other direction on the Earth and found it was the same thing. So my title was, My Clock Runs Faster Than Your Clock Because of the Dilation of Time, that if you look on a moving spaceship, as we'll talk about, it seems like the clocks run slower. It's also true that sticks on a spaceship appear to be shorter. So the other part of the title is, In My Rod is Longer Than Your Rod, but they wouldn't let me do that. So here's the short course in relativity, so bear with me. This will be the only equations that I'll show you. And this is high school physics, and I think we can do it. So you probably, if you've had high school physics when they talked about relativity, you've all seen this game before. Talk about a moving train. In fact, it has to be an awful lot faster than the train to see any relativistic effects. And the observer sitting in the station, say, seeing the train go by. And imagine having two mirrors on the train with a light beam bouncing back and forth, and the clock ticks every time the light bounces back and forth. So distance is equal to speed times time. So this is, say, centimeters equals centimeters per second times centimeters. Seconds equals centimeters. So this gives you a distance. Then the person sitting in the train station will see, instead of this, they'll see the mirror moving as the train goes by. And the mirror will move in proportion to the speed of the train. So if the train speed is v, and the time that we see for the ticking of the clock in the train station is t0, then the distance that the train will have traveled is v times t0. So we have a triangle, and everybody learned in high school geometry how to solve a triangle, just the good old Pythagorean theorem. So we have d squared is equal to little d squared plus L squared, and then if I substitute in ct sub 0, ct on the train, and I have this little equation, and then I just go through this equation and solve it, I get the following equations, which have a really long tail to them, which is that the observer sees the time on the train stretched by this gamma factor. And this relativistic gamma factor is this. It's 1 over the square root of 1 minus the relative velocity compared to light of this train squared. So you can see that when this thing is 0, then this is just 1, so the time is equal to the time in both places when the velocity is small. But when v gets close to c, this is near 1, this is near 0, and as you know, dividing by 0 gives you infinity. So then the gamma factor gets to be huge. So here is what happens. This is a graph of this. This is the velocity going between 0 velocity and the speed of light, and this gamma factor, for most of the time, even when you're going really quite fast, it's not doing much at all, but near the end, then it just goes crazy. And this has all kinds of implications. So now I'm going to talk about some applications of some consequences of relativity, and there'll be kind of a random scattering of a few things that we can talk about in this short amount of time. So the first thing that is so mind-boggling is that clocks do appear to run faster or slower depending on your system. And the clocks in the moving train do appear to be moving slower. And so we'll talk more about this in the next slide or two. Another thing that follows immediately from this is the idea of simultaneity is no longer so obvious. And the typical kind of physics 1 lecture demonstration of that is the person standing here seeing lightning hitting 2 trees simultaneously. From his point of view, persons on a very fast bus see them occurring at different times. So simultaneity, and you can make a much longer story about this, but simultaneity has a different interpretation when one understands relativity. And to go back, remember that the assumption at the start of this, and you can derive almost everything from the one assumption that the velocity of light is whatever it is, 3 times 10 to the 8th, 300 million meters per second, no matter where you measure it. You'll always get the same answer. So with a little more algebra and so on, you can write down that E is equal to mc squared and this gamma factor that I showed you before. Now, when gamma is not very much different from 1, when the velocity is low, I can write this as approximately mc squared plus 1/2 mv squared. Now, you all have heard E equal mc squared. That's what Einstein was famous for. E is equal to mc squared. But there's the rest of the term. There's the 1/2 mv squared, and that's the kinetic energy. 1/2 mv squared is when you run your car into a barrier at twice the speed, it's got 4 times the energy, going to do an awful lot more damage. Or if the brakes fail on your train, you're liable to come out the end of the station. The mc squared part was what was so mind-blowing at the turn of the century, and it still is, that energy and mass are the same thing. That somehow or other, if we can convert mass, we can get an astounding amount of energy out of it. C is a big number, so c squared is a really big number, and this energy is fantastic. And this is what led to things like nuclear reactors, which are much more efficient than chemical reactors in squeezing energy out of things. And it led to, for example, appropriate to talking about IFA events, the understanding of how the stars burn. We didn't know how the stars burn until 75 or 80 years ago or so. And we now have great models of how the stars burn and evolve. There are just vast implications all across science, and moreover, must be asserted to you that there's just no question that relativity works. There are some cranks around that are always saying, well, you know, blah, 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 Einstein, I don't know. But the facts are you just can't escape it. You just can't. So, next slide. So, I want to tell you about an example of how we can see right in this room tonight that relativity works. There's particles called muons that are made. Cosmic rays come in and hit the atmosphere. They make a flock of secondary particles. And then there are some longer-lived particles that continue on. And the main species that get to the surface of the Earth here are these things called muons, and my favorite subject of study, neutrinos, that I don't get to talk about tonight. And the muons are coming through us all the time here. There's about 100 muons per square meter per second going through us here at the surface of the Earth. And these muons have a lifetime. If you have one here in the laboratory, you measure the lifetime. These guys, their lifetime is about 2.2 microseconds. There it goes. So every time this guy beeps, there's a cosmic ray going through it. This is a little cosmic ray counter. There's 2 scintillation paddles here and photomultiplier tubes And so when a particle goes from here to here, in coincidence, there's a cosmic ray has come down all the way through the building, right on generally into the ground, and it's going click, click, click. You can see one every second or two, and just random. So this is a picture of that here. And I better turn it off before it drives everybody crazy. So these muons are pervasive, and the point here is that living 2.2 microseconds, traveling at the speed of light, they'd only go about 2,000 feet. They're made in the atmosphere up at a little higher than aircraft altitudes and so on, and they generally wouldn't make it to the surface of the Earth. But in fact, if the typical muon has 20 times its rest mass, this gamma factor is 20, so they live 44 microseconds. If you multiply that times the speed of light, they can travel from airplane altitudes down to the surface, and they get here. And in fact, there are higher energies, and they get way down deep in the ground, into the deepest tunnels in the ground. And people have even set up experiments. Some people from the University of Texas are setting up an experiment to X-ray one of the Mayan tombs using this technique. And it's been used in the past. Louis Alvarez and company in the great temple of Sephron in Egypt many years ago did the same thing, to look for hidden cavities. So these muons are here. The point of the message is simply that if it weren't for relativity, for the clock running slow, as we see it, in the muon, then it wouldn't live long enough to get to the surface of the Earth. So relativity is seen every day here on Earth. So here's a little fun. What would happen if you got onto a nice spaceship like the Enterprise here that had an acceleration of 1g, that's to say accelerating fast enough that it pressed you back in your seat by the equivalent of gravity, be comfortable, you'd enjoy life, and you start sailing away and keeping the pedal to the metal at 1g, how fast would you be going? Well, after, say, 2.337 years, the elapsed time on Earth would be 5.127 years, and the distance traveled would be 4.223 years, and you would be at Proxima Centauri, our nearest neighbor star. Okay, well, that's nice. So after 4 years or so, you'd be at the brightest star. You could be at the range of the brightest star. It's in a different direction, Vega. After 6.6 years, you'd be out to the Pleiades, which were a goodly ways out, 367 light years. But interestingly, now you're really picking up velocity. You're starting to get up near the speed of light. By the time 11 years has passed, you've reached a distance equivalent to going to the center of the galaxy. That would, of course, be a really bad idea because there's a lot of stuff down there, including a giant black hole, and you might regret having gone in that direction. Might be the end of your trip. If you went in another direction toward the Andromeda galaxy, our nearest major spiral galaxy, after only 15 years in your time on the spaceship, haven't gotten much older, sipping martinis, flying along, suddenly there's Andromeda. And you keep on cruising, and speed is picking up. But what's happening is your clock in the rest frame from here is getting slower and slower and slower. And things are starting to flash by. And carrying this on through here's our nearby Virgo cluster, here's the Coma cluster, 100 million light years out. And then finally, after only 25 or so years old, 25 or so years past, you'd be long enough that many of us would survive it, you would be at the edge of the observable universe. That's just astounding. You could live to see the whole universe. Little problem, because by the time you turned around and came back, if you could decelerate fast enough and so on, and came back, the galaxy might not be here. So here's a scheme of how to live forever. Well, not quite forever, but a long time. You've all heard that this big accelerator is being turned on Switzerland. There's the Alps, and it's underground here, crossing the border between France and Switzerland. And it'll accelerate protons, the nuclei of hydrogen, up to energy is about 10,000 times their rest mass. This famous gamma factor is 10,000. So, if you could ride with one of these protons, you could live a really, really long time. So, of course, it would be a little tough in a tight radius like that. So we'd have to make the accelerator much bigger, put it in space, say around the solar system. And you ride on this, you could survive for about 800,000 years on this. You still are only going to get 80 years in your own time. You can't do anything about that. You're stuck with whatever your lifetime is, 80, 100 years. 1 second on board the craft in this thing would be 2.8 hours on Earth. You could just see your friends growing old in one day. So the bad news is that even though the physics, I think, perfectly well permits all of this, the power to accelerate to these energies is far more than we could conceive of in this day and age. Still, sometime in the far future, who knows? Maybe we put capsules into some sort of orbit where intelligences manage to live for a really long time. Interesting to think about. Another little tidbit in this story is that, as you know, Mr. Einstein, the relativity was all about saying that the velocity of light is the same wherever you measure it. So here, on the spaceship, on the moon, center of the galaxy, whatever, you'll always get c, 310 to the 8th meters per second. But now we know that there is, in fact, one rest frame. And by rest frame, we mean the velocity with respect to everything else. We know there is one set of velocities which is really at rest in the universe. And through these measurements, starting in Kobe and along with more recent measurements, we saw that there was a big asymmetry. You'll hear more later about the variations in this that tell us about structure in the Big Bang. But this is looking back at the CMBRs, cosmic microwave background radiation, at the beginning of the universe, 13.7 billion years ago. But what we see is a big dipole, as we call it, dipole term. Big asymmetry because we're going in one direction and going away from the other direction. And we're moving at an amazing speed, 620 kilometers per second, in sort of an unobvious direction. It's not pointing toward anything in particular. Even though it's quite a good speed, it's about 1,000th of the speed of light. The famous gamma is 1.005. I have to stutter a lot to say that. So what it does mean, though, is that our clocks run slower by 15 seconds per year. You say, whoa, well, big deal. But heck, after a lifetime, you got an extra 2 minutes that way. So let's hear it for having a good, snappy solar system. Next. So here are some things that Mr. Einstein in relativity tells us, and general relativity tells us you can't do. Sadly for science fiction, a lot of these things. There was a young lady named Bright whose speed was far faster than light. She went out one day in a relative way and came home the previous night. I've heard another version of that, which I think is not appropriate for here. But in any case, you get in all kinds of trouble if you can go faster than the speed of light. You can't, for instance, this is a poster from Back to the Future, of course, you can't reverse time. Time flies, and it flies in only one direction, and there's not much you can do about it. You can run your clock backwards, but you can't change the flow of time, and we can't change the regularity of the flow of time. You can't beat the speed of light with any information. You often see in the press, somebody says, oh, we did an experiment, we got faster than the speed of light. But the thing you should ask them right away is, but did you transfer any information? I can make faster than the speed of light in this room by just wiggling this laser across the wall. That spot can move faster than the speed of light. Big deal. No information went at faster than the speed of light. So who knows what SCN is? Subspace Communication Network. Where are you Trekkies? This is the decoder for it here. So Captain Kirk couldn't talk to home. not very fast at any rate. So we don't see any chance for that. I have to make one caveat, though, which is that there are some theories with extra dimensions and so on that might allow some fooling with this, but as far as we know now, there's no way around it, absolutely no way around it. Another thing that people talk about are wormholes. You all remember Contact and Carl Sagan's novel and the movie. And people started working on the idea of wormholes, which is a connection in the multi-dimensional geometry that is between two places and that you might be able to jump from one place to another. It makes wonderful science fiction. But it seems as though it could perhaps be done, but it requires an infinite amount of energy and no information can pass through. So forget all those nice pictures of looking through into another part of space and time. It doesn't look like it can possibly work. Even more depressing is that a rapid dialogue with even the nearest stars is not going to be much fun. It won't be an exciting dialogue, as it takes 20 years or so round trip to even the nearest star into the galactic center. It'll take you 50,000 years to get a response. That's one slow conversation. So, down to the end, what things can you do? What can you do? One of the best examples of talking about the influence of relativity, both special and general relativity, is talking about these terrific devices, the global positioning system that probably some of you have in your cars, take hiking here and there. Our friends use for surveying, all kinds of things. Marking out the locations of plants, as my wife does. That these things depend upon both special and general relativity. This is distance in kilometers, so this is 40,000 kilometers out. And this is the fractional change in frequency relative to the Earth. And so it's about here is 1 part in 10 to the 10th. That's pretty big compared to the accuracy of clocks these days. And so at GPS and GLONASS, the Russian satellite system in the geostationary orbit, it's a pretty big effect. This effect is dominantly general relativity, folks. This effect down here is special relativity. And there's one place here where they offset each other. So we have to put those things in numerically every day, and there are more examples of that. So I say that reaching the conclusion, we certainly get to glory in the emerging understanding of our place in the universe. We've been through the trials of being at the center of the universe. We're learning that we went around the sun, learning that we are just a minor star on the outside of a so-so galaxy and outside of a big cluster, nowhere special in the universe. Now we're not even part of the dark matter, or let alone the dark energy that's the most part of the universe. We should be humbled, but it's incredible that we have come within the last 100 years to understand all of this stuff, from this astounding combination of elementary particle physics to cosmology, the smallest to the grandest scales. We're beginning to make sense of our place in this universe. And I say, but don't forget your friends. And I add one little caveat for you to think about, is that not much talked about, is that our physics, much as it describes many things in elementary particle physics and so on, does not have a role for the feedback effects of intelligence on the fate of the universe. So when you hear people talking about that, there's a very interesting little catch in all that might be important in the end. So I put in a cartoon about the arc of phylogeny of, we're talking about arcs or linear time. This is so here we are now. So I say, live fast and die old. Click.